like something that works. But it moves actually. Except now it's serious. But the other way is with your triples.
Yes.
But why? Why?
Where do we come from? Magic.
Yes.
Yeah.
In lack of a better name, to be honest. It's one of these things that posteriori, I was never happy with the name.
I
I
see.
don't like this kind of thing. But it's something magical happens. I can explain. I mean, there is something very special.
Yeah.
So you can say special, you can say magical, you can say extraordinary, you can give them a name also. Actually, a good name would have been Kaylee Triples if it hasn't been used for something.
It's very special in a sense because everyone else would have called it special, which makes a lot of special things.
Yeah, it's very like magic, special.
Yeah, exactly. It's very difficult.
I'm very embarrassed.
But it's very unique. Very unique. No, I'm just wondering. Yes, that's very cool. I think she will explain why it's magical, though.
Of course.
Right.
It's not easy. It's just
The third day of the conference, it's a great pleasure to introduce Enya Hsiao from the Max Planck Institute for Mathematics and the Sciences. Enya will talk us about all magical triples and maximal Higgs bundles.
Thank you very much, Georges, and I would like to start by thanking the organizers of the workshop for inviting me here, and I really want to give my big thanks to Takashi, who switched with me yesterday because I caught a cold and don't really have a voice. So let me know if you can't hear me because everything is going to come from this. Okay, so today I want to present some work on extending the framework of magical triples to include some non-magical triples that capture a Kavli correspondence for flexible components of non-two types. We'll review these things. So let's start by reviewing the theory of maximal Higgs bundles, and this will be our setup. So we've seen this many times this week already, but it will actually be a simple complexity in geometry with split forms. And we're gonna say that it has Cartan decomposition as such, and it's complexified Cartan decomposition. First line in the context. Yeah. We'll let sigma be a closed-oriented surface, and we'll fix a complex structure on sigma to take a compact Freeland surface, and we'll let K be its canonical line. Okay. So a GR Higgs bundle is a pair where P is a polymorphic H bundle and Phi is the Higgs flipped polymorphic section of the P H bundle twisted by the isotropic representation. And this is often presented in what follows. They will often sort of switch from one to the other with this pair where E is an associated vector. Usually, if G is a matrix, we take this in the first. And will let HGR be the configuration of Higgs pairs with that stability conditions, and will let MGR be the moduli space. It has stability conditions and Euclidean by the action of the gauge groups. You can think of it as isomorphism classes of fully stable G Higgs bundles up to the gauge group, which in this case is the smooth automorphisms of the H band. And the reason we want to study, or we're introducing these geometric bundles, is to study parent-height field theory which is the search for connected components in the character variety such that every representation of the component is discrete. And the classical example is when GR is equal to SL2 or PSL2. I guess PSL4, and then inside the character variety, there is a component. Actually, there are two copies of the same component called types. And every representation in the particle space is discrete. And the reason we're introducing GR Higgs bundles is, as Oscar mentioned the first day, there's homeomorphism between character variety and the moduli space of GR Higgs bundle. So we can study one with topological invariance with the other. And here's a baby case for the non-abelian Hodge correspondence. On the left-hand side, you pairs where of SO2R Higgs bundle with, in this case, E, the vector bundle is a line bundle plus its dual, and the Higgs field breaks to this off-diagonal form consisting of holomorphic sections beta and gamma. And this will correspond to the other non-abelian Hodge correspondence to SO2R representations. But if we look at it more finely, we ask the degree of L to be G minus 1, then this will correspond to the component in the character variety, the representational line, the Teichweiler space. If we fix K1 half, then the following bundle will be, it is a very special bundle that will occur later, and we call it the uniform case. And now notice that, which due to stability conditions, which I didn't really explain what it is, if degree of L is strictly greater than 0, then in order to prevent it from being a destabilized subbundle, we really need gamma to be a non-trivial, so non-zero section of this line bundle. And this condition then gives you an inequality that says that the degree of L is bounded above by G minus 1. And you do the same exercise if degree of L is strictly less than 0, and you notice that so degree of L is bounded below by 1 minus G. So in total, the absolute value of degree of L is bounded above by G minus 1, and the representations in the Teichweiler space then corresponds precisely to the time to where the degree of L achieves its maximal possible value. And so this phenomenon occurs because SL2R is what we call a Hermitian Lie group, and this sort of example actually occurs more generally for Hermitian Lie groups, and this is what we will now review. GR is a Hermitian Lie group if its symmetric space admits a complex structure that preserves the Riemannian metric. And the Lie algebra of a Hermitian Lie group, or one Lie algebra that's the algebra of a Hermitian Lie group, will be called Hermitian Lie algebra. Now, there's an important property of Hermitian Lie groups, and we call it that a Hermitian Lie group is of tube type if its symmetric space is isomorphic to a tube domain. So in the example from before, SL2R is actually a Hermitian symmetric space of tube type because it's SP2, isomorphic to SP2. And in this case, it's the symmetric space is isomorphic or homomorphic to the Siegel upper half. If we ask the Hermitian Lie algebra to be simple and of tube type, then there are only 5 possibilities. These 5. On the other hand, a Hermitian Lie group is of non-tube type if it's not of tube type. So in this camp, it admits up to conjugation a unique maximal subtube that is whose symmetric space is irreducible Hermitian of tubes. This means that the Lie algebra of G smaller case, so GT, is simple and is a simple Hermitian Lie algebra of tubes. But actually, if you take the normalizer of G small, GT, the normalizer of this, it's also going to be Hermitian of tube type. It's just that its symmetric space is not going to be irreducible. And the normalizer is going to be the maximal subgroup that is Hermitian of tube type. And this turns out to be important later. Okay. So if we look at the Lie algebra of a Hermitian Lie group, then, or of non-tube type, then this GT, HT, and MT sort of sits nicely inside the Z algebra. So there's actually a element in the complexification that induces a kind of involution, so that keeps the tube type, so the maximal tube part invariant. And this decomposition can then be seen as plus and minus eigenspace of that involution. And if the minus space is 0, then GR is 2. And if not, then you have some Kavli, this Hermitian Lie algebra sitting. And now the maximal subtube and its normalizer actually has some very nice relationships. So they differ by a subalgebra C hat, which can be seen by taking the Lie group. So you look at the maximal compact of this normalizer, maximal subtube, and you look at the part where it acts trivially on M sub T. And that gives you a subgroup C hat, and then the difference between the maximal subtube, so the simple Lie algebra, and this one that is not simple, is precisely given by the C hat. And that sort of extends onto the maximal, okay, this sort of. So here I listed down the list of simple Hermitian Lie algebras that are of non-tube type and looked at, and it's small tube. Just here, and then also the data of C hat, so that you can find out easily what G uppercase T, G capital T. And given a simple Hermitian Lie algebra, we can define the Toledo character by pairing an element in the complexified maximal subalgebra with minus ij, where j here is the almost complex structure, and this bracket, you can take it to be the killing. You sort of normalize this by the dual constant. And it is actually a theorem shown by, in the paper of Picard, Garcia Prada, and Rubio, that possibly up to a multiple, this Toledo character lives to a character. In the cases today, they always just live nicely. So you don't have to worry about it, but in case one is worried, then it's always up to. And now, given a GR Higgs bundle, you can twist this bundle part by the character. So this is an H bundle, and this character sends H to C. So you twist by this character, and you obtain a line bundle. And the Toledo numbers are defined by the degree of this. And then there's another theorem, well, it's sort of a generalization to more complex cases, but this was sort of first done case by case for the different Hermitian groups. That if you look at a polystable GR Higgs bundle, then the Toledo number of this bundle will be bounded above and below by the rank of this metric space times 2G minus 2. And to show this, actually, it's very important that E is polystable. Polystability is one ingredient that's used to show that this. So now that we have the Toledo invariant, we call a Higgs bundle maximal if its Toledo number is maximal. That's possible. Kind of like in the example, in the baby example before, with degree L. And now, under the non-abelian Hodge correspondence, the Toledo number of B actually corresponds to a different definition of the Toledo variant of the representation that corresponds to. And it's given by pairing the pullback of the Taylor class via the representation and pairing it with the fundamental class signal. And this Toledo, this function is continuous on the set of representations. And so this gives you, in fact, a topological variant. So it's in fact locally constant on each of the components of the moduli space. And so then it makes sense to say that a connected component can be, so a connected component are labeled by these Toledo numbers, and those ones that consist entirely of maximal G-Higgs bundles are called maximal components. And we say that N-max is the set of maximal polystable GR-Higgs bundles. And here's a theorem that was proven by Berger-Yuzzi and Lienhardt, that maximal components are higher diagonal spaces in the GR character group. And this statement is for Hermitian groups of tube type and of non-tube. They're all higher diagonals. Okay, but as of the existing literature, the behavior of the maximal components actually split into two camps. If GR is simple and of tube type, and there is a Cayley correspondence that says that the maximal GR Higgs bundles are actually isomorphic to H squared twisted H star Higgs bundles, where H star is the non-compact dual of H. You can sort of unravel a factor of R cross, and then it's sort of isomorphic to this, as we'll see in another formulation later. On the other hand, if GR is simple enough non-tube type, then what one can say is that a maximal polystable GR Higgs bundle is never sort of strictly stable, but rather they're strictly semi-stable, and they're reduced to a maximal polystable GT Higgs bundle. But remember that GT is the maximal Hermitian subgroup, and it sort of relates to the maximal subtube in the following way, where you quotient out by possible finite. And so the question of today is there a Cayley correspondence for maximal components of non-tube type? So for this cap, can we describe these maximal GR Higgs bundles in some way that is similar to the one above? This was not known before, and the answer is yes. So in order to do that, let's review a more general theory of these Cayley correspondence that came up sort of in the past maybe 5-6 years. It was developed by Oscar and his collaborators. And let's look at the theory of magical triples, which later then becomes even magical triples. Okay. So first of all, an SL2 triple is an embedding in SL2 G. We can study SL2 triples, orbits thereof. So if you take G orbits of these SL2 triples, then they're in bijection with orbits of the nilpotent element. And this is why sometimes it's equivalent to say, when you look at an SL2 triple, it's equivalent to say that it's some kind of nilpotent orbit. And this bijection also holds when GR is a real Lie group, when we look at real nilpotent orbits. And what we really want to study is SL2 triples or orbits thereof in a real Lie group. And to do that, there's actually a very nice correspondence called the Sakiguchi correspondence that says that real nilpotent orbits can be studied by H orbits of nilpotent elements that are in N. But recall that, so here we start with GR and then we sort of complexify the Cartan decomposition. So H is complexified maximal subgroup and M is sort of this complexified part in the Cartan decomposition. And under this correspondence, then, on the right-hand side, you have real triples that are called Cayley triples, and they correspond to normal triples. Okay. And complex and real simple nilpotent orbits, they're characterized by their weighted Dinkin diagram, and here's some examples. So actually, if you know, this one is a magical or even magical triple, and this one, as we will explain now, will be an automagical triple, but these two are not the same SL2 triple, and they correspond to distinct nilpotent orbits of SL4C. So in most cases, actually, these weighted Dinkin diagrams are complete invariant of the nilpotent orbit, but unfortunately not so when you're doing a real Hermitian Lie group. So at the moment, I just say that they're characterized. Okay. Are there any questions so far? Okay. So once you have an SL2 triple, it induces two compatible decompositions. On one hand, in the SL2 triple, you can think of it induced by the adjoint action, G will become an SL2 representation, SL2C representation in particular. We know the SL2C representations or sort of decompose into irreducible parts. So you can write G as some kind of sum of the irreducible SL2C representations, where it's possible that you have multiple copies of the same one. So this is what the NJ is for. So on the other hand, you can also think about the semi-simple element in your SL2. So this H is given by the SL2, and you think about the weight spaces of H, and this gives you a Z rating on your Lie algebra. And the Lie algebra also splits it into directs these weight spaces. And these two decompositions are compatible in the sense that it gives you a bi-decomposition where you can sort of write it as the double sum here. And each of these spaces is actually equivalent to, we'll see this in a bit, in the next slide actually, that you can take the highest weight spaces, you lower them by k times by the add f, and you actually get this space. So you can think of this equivalent to this. And now an SL2 triple is called even if, and you look at these weight spaces, all the weights J are even, or equivalently, actually, all of the weight K are even, and odd, otherwise, it contains Okay, so here's an example of an even SL2 triple. So let's look at the principal SL2 triple and SL3C. Actually, the label here tells you what SL2 triple it's going to be. So 2 is the difference between these, so 2 minus 0 is 2, and then the second 2 is 2 minus minus 2, this is 2. And there's a recipe that tells you what E is going to look like. So from this, you can actually entirely obtain the information of E, H, F. And now one thing is you can look at the centralizer of E, or kernel of add E, and you realize that it has 2 dimensions. It consists of these two, and so coincidentally, this is how you tell that this is a principal SL2 triple, because you want the nilpotent to be regular. This means that the dimensions that E is equal to the rank of SL3C, which is 2. So two things here. And now this element is just E. So when you lower it, you get E, and then H, and then F. So this is a copy of W2. And then this one is another highest weight space. So it corresponds to weight 4 under that H, and then you lower it 4 times, and then you see a copy of W. So the decomposition on the one hand is G is equal to W2 plus W4, or G is equal to G minus 4, and so on. And each of these dots, in this particular case, is the one-dimensional space in the bi-decomposition. And you can also think of it as coming from the highest weight space and being lowered. I forgot to mention the highest weight spaces are captured by the centralizer of E. And this is an even SL2 triple because all of the weights are even. Okay, so I've introduced this. An SL2 triple is called magical if the a priori vector space involution. We'll see this more concretely later. So this is a vector space involution that says if X is in V0 or W0, in that case, it's just the same. And otherwise, it will act as -1 on the highest weight spaces. So when K is equal to 0, it will act as -1. And as you apply the lowering operator, it sort of alternates. So it's -1 plus 1 minus 1. We'll see this. And the point is, the definition says that such an SL2 triple is magical if this vector space involution is indeed, in fact, a Lie algebra. And now rho is magical, and there is a real formula, so meaning this is a Lie algebra, so this is a complex linear Lie algebra involution. In fact, there is a real form associated to this. Actually, up to fixing a compact real form, there's a real form associated to this, the algebra involution, and the fixed points of that real form equal the canonical real form. So equivalently, real triple is magical if so it comes with a Cartan involution, so this is an involution, you sort of complexify it to the level of the algebras, and it's magical if, with respect to this complexified Cartan involution, it acts as -1 on the highest weight spaces, and 1, so identity of the 0 is V0. So let's take a look at what we've done before. Okay, so in particular, maybe let me first mention, in particular, if you have a magical triple of G, then you get a canonical real form, and the triple will be a magical triple of the canonical real form. And conversely, if you have a magical triple of some really algebra, it's you can complexify that via the Cayley correspondence, and you get so sort of it's equivalent which perspective you take. So let's look at this principal triple that we discussed before. So let's forget the red spots, red things for now. The magical involution says you start with, so you look at V0. There's no V0 in this case. You start with the highest weight spaces, then it will be minus. Then it will be plus, minus, plus, minus. And there's one easy method to check whether this SL2 triple is magical. And is, namely, you require that the centralizer of rho, which in this case is trivial, is in H. So it has to be labeled plus, and you require that this dimension formula holds. So you can check. Dimension of M is the number of minuses, which is equal to 5, and dimension of H is the number of pluses, which is equal to 3. In this case, it's 5 minus 3 equals to the highest weight space is minus 2 times dimension. Say there's 2 minus 0, so it's 2. And from this, you can also see that the canonical real form has 3 dimensions. So it's the dimension of H, complex dimension of H is equal to 3. So you look into the real forms of SL3C and you realize, okay, SL3R is the only one that has canonical real form with whose maximal compact sub-algebra is 3 dimensions. Okay, so it ought to be a bit faster. Here's a second example of a magical triple, namely you look at G is equal to S, P2, and C, and you look at these blocks. And you obtain that the SL2 decomposition looks as such. And this is actually a Hermitian Lie group of 2 times. And the magical involution, you put the minuses and plus on here, and then you check that indeed the dimension formula holds, and you have that the centralizer of the representation is all labeled with a plus, and they're all and this canonical real form has maximal compact subalgebra n squared, and you check that, well, this has to be the split real form SP2 and R that has maximal compact subalgebra UN. Okay, that's the only one with this. And now let's look at a non-magical. So if you look at this is a different matched SL2 triple of SL3C, and it looks like this, E, H, and F. And it actually, if you forget the middle part, this is an embedding of the standard SL2 triple into SL3C. And then compute the centralizer, and you see that it has 4 dimensions. So this is not the principal SL2 triple, it's substantially different. And you look at its decomposition, and you put the magical involution. And you realize that this is not a magical triple because you can compute that sigma rho of the bracket of these 2 elements. That this should have negative parity, but if you compute the bracket, it has something as positive parity. So the sigma rho does not preserve the bracket, and so it's not a linear triple. But more faster way, you check the criterion, you see that there's 4 minuses and 4 pluses, so 4 minus 4 is equal to 0, which is not equal to 2. Okay. And so there's a classification, so magical SL2 triple has been classified by Oscar and his collaborators, and it says the following: a simple real form admits a magical triple if and only if it belongs to one of the 4 families. And coincidentally, if you check the list of simple real forms that admits a theta positive structure, and you see that it admits a magical triple if and only if it admits a theta positive structure. And this sort of is very interesting as it leads us, I am skipping, so okay. It leads us to the Cayley correspondence, which is in 2 slides. In order to describe the Cayley correspondence, first, let me set up a little bit the Slodemy slides. So if you have an SL2 triple, you can push forward this uniformizing SL2 Higgs problem via this SL2 triple. You get some we also call it the uniformizing Higgs process, ETF. And now, using this uniformizing Higgs bundle, you can then construct a Sloterdijk map that sends an object in the Sloterdijk category, which is pairs of a C bundle. So C also comes from the data row. C is a centralized row, and some sections, which also depends on the SL2 decomposition. You can send these pairs of things into G Higgs pairs. This is sort of a bit of an sort of not so nice formula for now, but the point is that when you restrict this map, so this map a priori lands in G Higgs pairs, but when you restrict this to GR Higgs pairs, this map descends, you restrict to the pre-image of these, this descends nicely to an open, closed, injective map of moduli spaces. And the important thing is, image of this map is a union of higher titular space. So at least this is true for the first three families, and we strongly believe that this is the case for the fourth family, which is the exception of these groups, as a union of higher titular space. However, in this formulation, so this led to the formulation of the following conjectures, is that a connected component is a higher titular space, if and only if it is in the image of some of this Sloterdijk size. So namely, if and only if GR admits a magical triple and this component lands in the image of psi. And C is not the maximum, so if and only if this is true and C is not the maximum component of a Hermitian Lie group of non-2 type, because sort of somehow in the formulations, this case is not captured. And the point of this talk, which I have 15 minutes for, is that actually these components are also captured by such a Cayley correspondence. And in order to understand that, we need to introduce odd magical triples. Okay, so let's go back and look again at the example of this non-magical triple before. This isn't, and the point is that this is actually an odd magical triple because we look again at this non-magical triple. Sorry, I think there's a typo. So the magical involution says that all of the highest weight spaces are minus, but if you actually switch one of the plus and minus, so it's actually not minus, but rather you switch these two, then you do get a Lie algebra involution. And the real form associated to this involution is S212. It's Hermitian Lie algebra of non-2 type. And in this case, the maximal subtube is SU11, which is SL2R, and the normalizer of the maximal subtube is SU11 plus U1. So you can see this sort of sitting, the GT sort of sitting nicely right here in the even part of the decomposition. So this is SU11 and this is. And furthermore, if you look at row restricted just to the even part, you see that it is a magical triple because it's the highest, non-trivial highest weight space minus and the centralizer is plus. And this sort of is a phenomenon that happens because row is induced by trivially embedding the magical triple of this SU11, so it's a Hermitian Lie group of 2 type into this Hermitian Lie group of non-2 type. And so this sort of happens generally, and this is the baby case, it sort of happens generally. And so we can sort of loosen the definition of a magical triple by saying that it's an extended magical triple if there is a complex linear Lie algebra involution that acts as the magical, acts like the magical involution on the even weight space. So we sort of say, okay, I don't care about what happens in the odd weight space, I just care about what happens in the even weight space. And if this is the case, then any extended magical triple that is not captured by the previous definition must be odd, because if it is even, then the definition sort of coincides with the previous magical triple definition. So we call whatever is not captured odd magical triples. And we adjust the formula, checking that it's a magical triple by replacing the highest weight spaces by G0. So what happens here is you see that G0 coincides with the even highest weight spaces, and the odd weight spaces sort of skip over by 1, so it doesn't really affect G0. So in order to capture these ones, you really just need a formula, dimension formula for G0. So if you do this, then you will see that that there are only 3 odd magical triples. If your GR is a simple real form, there are only 3 odd magical triples, and they correspond to when GR is a Hermitian Lie algebra of non-2 type. And here I wrote down what the triple is, or the sort of Cayley transform of the triple are. They look like this. Okay. And so this, using this, one can write down in similar fashion a Cayley correspondence for a non-2 type. Okay. So to do that, let's first understand the pseudo slice of an odd magic. Okay. So some properties of odd magic. First one is that since we've isolated there are only 3, you can just check case by case. In each of these cases, an odd magical triple is induced by trivially embedding the even magical triple of the maximal subtube into GR. And then when you restrict to this normalizer of the subtube, you see that it restricts to an even magical triple of the normalizer. This is sort of where all the magic happens, I guess. So recall that the Sloterdijk map is sending pairs of objects like this into pairs of G Higgs pairs. And here's a statement that says that if you take an odd magical triple, so if GR is Hermitian of non-2 type, then the Sloterdijk map, when you restrict it to the set of polystable GR Higgs bundles, will map into the maximal GR Higgs bundles. And I aim to sort of try to sketch why that is the case. So first you check that what the restricted Sloterdijk map, so the image is, somehow the image consists of elements of this form. This happens when you restrict from a G Higgs pair to a GR Higgs pair, that the phi C has to vanish, and that the G Higgs bundle has to be reduced, you can reducible to an H bundle. And to check that the image indeed has our maximal, you just need to check the Toledo number. So you check the Toledo number, and the Toledo number sort of splits off into 2 parts. And this is because C, actually didn't write this, but C also splits into a copy of CT. So this is the centralizer of the magical triple of this maximal subtube plus some C hat. And this part, because of the Cayley correspondence, already has maximal Toledo number. And this sort of forces that the second summand to be 0, or if this second summand is not 0, then you can just take another bundle. Using the Cayley correspondence, you can find that this is maximal in the other direction, so sort of minimal. And then that will somehow violate maximality. So this part has to be 0, and this summand has maximal Toledo number. And so you conclude that such bundles in the image indeed have maximal Toledo number, so they are indeed maximal. It maps into, at the moment, the maximal polystable GR Higgs. But conversely, if you take a maximal, this is showing that it's onto, if you take a maximal polystable GR Higgs bundle, then by the statement that was shown before, it reduces to a maximal GT Higgs bundle. And now so the GR sort of splits into the 2 parts. And now the point is just you put them together, and since C hat R is by definition of these odd magical triples compact, the Higgs field vanishes. So you then put these 2 things together, and you see that indeed this is going to be in the image some element still be captured. But here I sort of swept under the rug and said, as you always need to quotient out the finite solution. Okay. So here's a statement. Also did not mention G tilde this, sorry, G tilde. So let me just. So the conclusion is that there exists a Cayley correspondence that is an open enclosing and an injective, I should have it here, injective map of moduli spaces. From this factor, you can equivalently think about this as some K2 twisted of the non-compact tool of the maximal subtube, or the normalizer of the maximal subtube, into the maximal components of GR, where GR is Hermitian of non-2. And one example here is previously we've seen the case where you have SUNN, where it will be K2 twisted SLNC, and there's nothing here because Q is equal to P. But when you have SUPQ, then you get this extra factor, and this factor corresponds exactly to the C hat, which is, so this C hat right here, that shows up. It's sort of like a small modification. And finally, in the last 5 minutes, I want to say that actually, with these extended magical triples, so the even and the odd ones, you can give then a characterization of magical triples or extended magical triples using the intersection, sort of the dimension of the intersection with the moduli, of the Slodowee slice with the moduli space. Or rather, let's call the Slodowee slice the image of such a map. So such a map, so this psi hat map does not depend on rho being a magical triple. This sort of is a Slodowee map that exists for any SL2 triple. And we look at the image of this, which is G Higgs pairs. We're restricted to GR Higgs pairs, and then sort of look at the equivalence classes of those in MGR. We call this the Slodowee slice of rho in MGR. And here's the point, is that if you assume the genus of X is big enough, then you can use a theorem of Kin and Pan-Su, which I'll explain in below, and show that any SL2 triples, you run through all of the SL2 triples, and you see that such an SL2 triple is an extended magical triple if and only if this Slodowee slice is a union of connected components. So on the one hand, we already have the Cayley correspondence that tells us if you have an extended magical triple, then it's going to be a union of connected components. So what one needs to show is that if it's not, if it's union of connected components, well, one needs to show that if it's not an extended magical triple, there can't be a union of connected components. So quickly run through the proof, and so you do the contour, so proof by contradiction, I suppose. We just need to show one direction. So you suppose that your Slodowee slice is a union of connected components. And first you show a small lemma that says that the components, you can count the dimension of the Slodowee slice and achieves expected dimension if and only if you're starting with even magical triple. Okay, so now if all of the connected components achieve expected dimension, then you must have started with even magical triple. But if not, then there are some components that has strictly smaller dimension, the expected dimension. And here's where we use a result of Kim Pan-Su, which uses the genus argument, even though they say that there should be a cleaner argument that doesn't really assume that, but they expect the statement to be true without that condition. You can deduce that that this Slodowee slice, where the connected components must be maximal components of some permission you could choose. So essentially, those are the only cases where the character variety has smaller dimension than the expected dimension. And okay, so suppose now rho hat is not an odd magical triple, then all you have to do is to cook up something that is such that slow rho doesn't map into the image. What do we say? That there is a maximal, there is some, you just have to cook up some Higgs bundle that is maximal but not in the image of the Slodowee slice. And then you're down, you have a contradiction because you know there has to be connected union of maximal components, but you found a maximal Higgs bundle that's not. Okay. And then finally, in the last 1 minute, I want to say what happens to this particular subspace of the algebra. So you see that here we said that for maximal GR Higgs bundle, you only care about the GT part. It's just this part, the blue part. But here you also have a highest weight space that is labeled minus. So what happens to this weight space? Well, it turns out that when you are studying Hermitian Lie groups of non-tube type, because there is this dimension, there is this reduction to G big T, you don't care about this one, because if you assume that your bundle is polystable, then this any holomorphic sections in here will just automatically be isomorphic to the one where it's zero. So this dimension doesn't like, if you now take a different real form, so if you don't take the canonical form, you take SL3R, you take SL3R, then the Slodowee slice. So you take the Slodowee map restricted to SL3R, then this thing shows up. And this turns out to be a cyclic Higgs bundle that is studied by Coulomb and Samuel. And they show that those cyclic Higgs bundles, so you take holomorphic sections in this particular subspace, correspond to NOS representations. And this actually happens more. You can take an ant-matching triple, and you can look at the paths where this odd patch that sort of is skipped over when you study Hermitian groups. You take cyclic Higgs bundles in, well, I guess SLNR, they also consider other groups. And you see that the Slodowee slice there actually correspond to some NOS representations with a suitable theta. And that's something that I think that I don't understand, or don't know what the bigger picture is. Yeah, this is what I have for figuring it.
Very much. Questions for Enya?
So the statement that the real forms for which the only ones for which there is this dimension being smaller than expected, the statement is strictly speaking is for the canonical forms, right? You could ask that if that for other real forms that are not.
You mean
here.
for Kim Pan-Su's result?
No, Pansu, I'm talking about this. Yeah, the statement that the only real forms for which there is this rigidity phenomenon.
Yeah.
So your statement was about the real forms that are obtained from magical principles, right? But you could ask what happens for other real forms.
So not simple real forms.
Simple real
still
forms,
simple real
but
forms.
they're not arise from a magical triple, right? I mean, there are many, right?
Yes.
And so you can ask, why is it that there are no components that have a smaller dimension?
Yes, but I think Kim Pan-Su's argument is for general rigidity's theorem, not just for it doesn't depend on the
this
magical.
hypothesis, I guess.
Yeah. Maybe I should clarify a bit with you later.
Yes.
What you were saying.
More questions? Wait. Disappeared. Sorry. Maybe I can ask. So does your classification of the automagical triples exhaust the non-tube type cases?
Yes.
That's all, those three.
Yeah, there are only three. And those are the three. Yeah. So the Lie algebras are much simpler. So if you look at only simple Lie algebras, but when you look at Lie groups, and it's the same as with the magical case. You can have covers and quotients that all have the same Lie algebra. But when you to the algebra level, there's only three, and you find that those are the three that's sitting there.
Do you believe there are odd magical triples for real forms that are not Hermitian?
No.
So
if you check through them, there are none.
Like any other real forms.
Well, I mean, so this is
Exception.
if you look at the simple real forms, then they're not. So you check through all of them, and they don't satisfy the criteria.
Yeah, I think this is really what the classification says.
That's the classification, right?
But type ones are Hermitian.
The reason is that you don't. The funny thing is that this is a magical triple, so even magical triple for a subalgebra GT that is not simple, that sits inside this the simple. So you see, yeah, that was the point. why this works out so cleanly is because you have an even magical triple, and when you classify even magical triples, you only look at simple real forms. But this GT is not simple real forms, so you sort of don't see it there, but it's actually sitting in there. But so I guess one can extend this by saying if you have so maybe there are other similar phenomenons where you have some kind of subalgebra and you have some magical triple of that subalgebra. So in this case, I don't know if it actually exists, if this excludes those, and then you can still study. So there will then be a Cayley curse.
Okay, if there are no more questions, let's thank Enya again. And we resume at 11?
11:15.
11:15. Okay, sorry.
My accent was weird. Not sure because